Hello everyone. This is the 10th tutorial session of the subject Mechanics of Solids. I had to re-record a portion because the file had got corrupted, so I started the recording all over again. So, I am Sukanya Karmakar, a fourth year PhD student in the Department of Civil Engineering at IIT Kanpur. This is my email ID. So, if you have any doubts in, I'll just adjust my mic. If you have any doubts in the content which has been covered earlier, and you have any doubt in the assignment or the solution which has been given to you, you are free to drop an email. I'll be happy to help you. So today we'll be discussing questions based on the concepts which were covered in the week 10 uh, of the subject, which is mainly focusing on calculation of shear stresses and the combined state of stresses, but that is on a body when you apply normal force, then a torque. The torque produces shear stress, or application of just shear force, which produces the shear stress. Application of a moment, bending moment, which generates a normal stress, and basically combination of these state of stresses. So let's start the session. Okay, since a part of my tutorial got corrupted, we had already discussed a question. I'll revisit that question again and then we'll move on to the other questions. So, so this is the first question. I'll just make the thing full screen. Okay, so in this question, you have a beam A, B, C, D, and which is subjected to a UDL load, and the cross section of the beam is given. The height is h and the width is v, and the spans of the various spans have been mentioned. You have to determine the ratio of the maximum values of the shearing and the normal stresses in the beam. So for a rectangular section, we know that this is how the distribution of the shear stress looks like, and this is how the distribution of bending stress looks like. So for calculating the maximum value of shearing and normal stresses, you for the bending stress, you will calculate uh, the stresses here. Sorry, you will calculate the value of the bending stress at the at the top, because that is the point where the bending stress is maximum. And for the shear stress, you will calculate it at the and for the shear stress, you will calculate it at the neutral axis. At the neutral axis, in a rectangular cross section, you get the maximum shearing stress. So this is the beam which has been given to you. So in this beam, you can calculate the values of uh, you need to know the values of the maximum shear force and the maximum bending moment. So let's draw the shear force diagram and bending moment diagram. So to calculate that, you need the support reactions. So what will you need to calculate the support reaction at B and at C? So we can see that the beam is symmetrical about this line XX. So the reactions have to be equal. So what is the total load acting on the structure? W is the intensity and the total length of the beam is L. So into L is the total load acting on the structure, and there are two reactions which have are equal. So the reaction forces are WL by 2 and WL by 2. So once you know them, you can calculate the shear force diagram. So the intensity of the load is W, and this length is WL by 4. So you have a shear force of WL by 4 here. and similarly a shear force of WL by 4 here. Then you have a constant reaction of WL by 2. So this line moves up, similarly this line moves down, and you can join them. This is how you can calculate construct the shear force diagram. Then how will you construct the bending moment diagram? So for the overhang, we have a bending moment, um, mm, like the curve will be like this, similar to that of a cantilever. And what will be the intensity, the value of the moment? The intensity W into the span length, that is WL by 4, into the distance of the CG, that is L by 8. So the bending moment is WL square by 32. This is the bending moment here, here, and here. Now, what will be the distribution of the bending moment within the span? So let's consider this, that you have a span BC with the UDL, and these are the two concentrated moments because of the overhang. You can break this system into a simply supported moment with the UDL, and then the span with the two concentrated moments. For the two moments, the bending moment will be like this, and for the UDL, it will be like this. The span is L by 2, so the bending moment at the center is WL square by 32. And here the bending moment is WL square by 32 hogging, and here is this because of the UDL, it is WL square by 32 sagging bending moment. So the net bending moment at the center comes out to be 0. So the distribution is like this. So from by drawing the shear force diagram and the bending moment diagram, we get the uh, we get the maximum shear force and the maximum bending moment, which in the beam. Next, from so as I told you, we get the maximum shear force value to be equal to WL by 4. Then we have to calculate the maximum shear stress. So just use the formula, which is VQ by IZZ into B. So V is the maximum shear force. Q is so where is the maximum shear stress? So uh, it is like at the neutral axis, and the neutral axis is passing through the centroid in this case. So here, Q is the first moment of area of the shaded portion, that is between the neutral axis and the topmost surface of the cross section. So the first moment of area will be the area of the shaded area, which is B into H by 2 into the centroidal position from the neutral axis, which is H by 4. So this is how you get Q. Then IZZ is BH by 12 into B. So this, when you simplify, this is the value of the maximum shear stress. Now we have to calculate the maximum normal stress. For that, we need the maximum bending moment. So the maximum bending moment is WL square by 32. So we get this. So maximum normal stress is M into Y by IZZ. Y, what is Y here? It is the point where you get the maximum normal stress, uh, since you need to maximize it value. Where is the maximum normal stress maximum? It is at the surface. So Y, where you have to basically maximize Y. What can be the maximum value of Y? Y is being measured from this neutral axis. It is Y is equal to H by 2. So just substitute it into this equation. You will get 3 by 16 WL square by BH square. Then you can take the ratio of maximum shear stress to the maximum normal stress, and you get this value. So in other words, you have developed a relationship between the maximum shear stress, the maximum normal stress, uh, the H, that is the depth of the beam, and the span of the beam. Okay. A continuation of the first question. This is, you have to determine the depth H and the width B of the beam of the question one, knowing that, and the data has been supplied, that the length of the beam is 5 meter, the intensity of the loading is 8 kilonewton per meter, tau max is 1.08 MPa, and sigma max is 12 MPa. So, we know that the using the expression which we just developed. In that expression, you know what is the value of maximum shear stress, what is the value of maximum normal stress, and you know what is the length of the beam. So from here you can easily calculate h, that is the height of the cross section. If you substitute the values with proper units, you will get the value of h to be 0.225 meter. Then you need to find h has been calculated, that is the depth of the cross section. Now you have to calculate the width of the cross section. How will you calculate the width of the cross section? You can use this expression, that maximum shear stress is equal to 3 by 8 WL by BH. You know all the values, just substitute them and you will get the value of B to be this number. Okay. Now this question is which I had just started. So we'll pick up, like I'll start writing down the solutions from here. So you have a beam having the cross section shown in the figure, and it is subjected to a vertical shear force V. You have to determine the horizontal line along which the shearing stress is maximum. So we'll first write down the expression for shearing stress and then we'll maximize it. How do we maximize a function? We'll equate its derivative to be zero, and on that point we can judge whether it is attaining, the function is attaining the maximum value or the minimum value. And also we have to determine the constant k in the following expression for the maximum shear stress, where you have the expression of the format that now max is equal to k into V by A. V by A is basically average shear stress. So we'll have to calculate the value of the parameter k. So this is how you can approach the question. That, sorry. So this height is h, this height is h, this width is p. So the entire area is half base into height for one triangle into 2. So the total area is B into H. And moment of inertia is equal to about this line. It is 1 by 12 B into H cube. Since there are two triangles, so into 2. So it is BH cube by 6. So these are two things which you can keep handy. Now, this is the diamond which you have, diamond cross section. This is height h. Suppose this is, measuring the y distance from this tip. This distance is y. So centroid, where will be the centroid of this triangle located? It will be at, from this edge, it will be 2 by 3y. Okay. Now, so for a cut at location y, where y is less than equal to h, you need to write out the expression for the area. Then we'll write down the expression for q, and then we'll write down the expression for shear stress. Okay. So for a cut at location y, where y is less than equal to h, what is the area of the shaded portion? It will be half into height is y. So you need to find out this base distance. So the base distance, just use similarity of triangle. I'll just mark it A, B, C, D, and E. Now use similarity of triangle between the triangle ABC and ADE. So from there you can write B by H is equal to DE by Y. So DE is equal to BY by H. So let's use this BY by H. So the area comes out to be BY square by 2H. Then you need to write the statement Q. Q is first moment of area of the shaded portion. So what is the area of this? Uh, what is the area? Area is by square by 2h multiplied by uh, the distance of the centroid of the shaded portion from the neutral axis. So how much is this distance? This distance will be the total distance h minus 2 by 3y. So this is h minus 2 by 3y. So h minus 2 by 3y. So this simplifies to by square by 2 minus by cube by 3h. Okay. Now I want to write down the expression for shear stress. So tau at distance y, it is VQ by I into the width. Let me call the width using T because B is already a parameter in the calculation. So shear stress is V. Then we have to substitute the value of Q, which is by square by 2 minus by cube by 3h divided by I. I is bh cube by 6. So 6 by bh cube into T. And we just calculated the width to be by h. So by h. Now you can simplify this to be V by you can take out B common from this. And you can take by square common and you have a 6 outside, so let's take that inside. I'll take by common, so I have a y. I take 6 inside. So this will simplify to be v by bh 3 times y by h minus 2 times y by h square. Now we have to find the location where this shear stress is maximizing. So we'll take the derivative of this and we'll equate it to 0. we'll do d tau by dy is equal to 0. So that will be v by bh. So from here, sorry, from here we get that 4y by h squared is equal to 3h, or in other words, y is equal to 3 by 4h. Y is equal to 3 by 4h, or from the neutral axis at a distance of 1 by 4th h, you get the maximum value of shear stress. Or at a distance of Now we'll try to answer the second part of the question. That is, we have to determine the constant K in the following expression for the maximum shear stress. Tau max is equal to KV by A. So first we need to find out the maximum value of the shear stress. So we know the location of the maximum shear stress, and and we know the expression. So let's just substitute it and calculate the maximum value of shear stress. This is expression 3 into y by h into 2 of y by 8 into whole square. Just substitute y is equal to 3 by 4h. So this you will get to be 9 by 8 v by dh, and your area is, so in other words, this is v by a 9 by 8, and 9 by 8 is equal to 1.125 tau v by a. So the value of the constant is 1.125. Okay, I hope this question is clear. So let's move on to the next question. So this was the third question. So let's move on to the fourth question. So you have a beam whose cross section is, basically it's a rod of diameter d. It is supported by smooth bearings at A and B. So it is supported at a bearing at A, and that only exert vertical reactions on the shaft. You have to determine the absolute maximum bending moment along the beam and the intensity of the load is something like this: 12 kilonewton per meter. So you have to determine the absolute maximum bending moment along the beam. Then, if the diameter of the rod is 90 mm, you have to determine the absolute maximum bending stress in the beam. If D is equal to 90 mm, I forgot to write down the span. If D is equal to 90 mm, you have to determine the absolute maximum bending stress in the beam. I'll give you around uh, 2-3 minutes to think about this question, and then we'll start solving it. Okay, let's solve this question. So first, we'll find out the reactions. We know that at point A and B, there are only two vertical reactions. So first, we'll determine these two reactions. Then what will we do? We'll try to draw, we'll try to write down, draw the bending moment diagram or write an expression for it, and we'll calculate the maximum bending moment. And the point where we have the maximum bending moment, there we'll get the maximum bending stress on the like on at that point. Uh, you'll have that cross section of the rod, which is circular cross section, and the maximum bending stress will occur at the at d is equal to at radius is equal to d by 2. That is on the surface of the rod. You will have the maximum bending stress. Okay. So till here you have a uniformly distributed load of 12 kilonewton per meter, but here you have a triangular distribution. Okay, let this be AY and this is BY. This span length is 3 meter and this span length is 1.5 meter. Right. Now I will calculate BY. While for calculating BY, let's take the moment about point A. So summation of moment about point A is equal to 0. So is equal to by, okay, into 3, okay, minus I am taking anti-clockwise to be positive, minus because of the UDL intensity is 12 into 3 into 1.5. This will generate a clockwise moment, so negative, minus half into base is 1.5 into height is 12, and it is at a distance of the CG from B is at a distance of 1.5 by 3 plus 3 meter. So this is equal to 0. From here, we can calculate By to be equal to 28.5 kilonewton. Now, we have to find the value of Ay. So again, you can take the moment about point B, or you can simply use summation of force in the vertical direction to be 0. So let's use summation of force in the vertical direction to be 0. Then AY plus BY is equal to 12 into 3 plus half into base is 1.5 into 12. So from here AY is equal to 12 into 3 plus half into 1.5 into 12 minus 28.5. So this comes out to be 16.5 kilonewton. So AY comes out to be 16.5 kilonewton. From now we can simply write down the expression of for the bending moment. So So AY is 16.5 kilonewton and this is 28.5 kilonewton. If I This is A and B. So qualitatively, if I try to draw the bending moment diagram, the bending moment diagram will be something like this, right? Here, what will be the value of bending moment? Here, the value of bending moment will be half into base is 1.5 into height is 12 into 1.5 by 3. So this value comes out to be, I'll just plug in the values. It is 4.5 kilonewton meter. And here your expression for bending moment when x varies between 0 and 3 and x is measured from here. X varies between 0 and 3. Mx is equal to the reaction AY, which is 16.5x minus because of the UDL. So x square by 2, W into x square by 2, so 12 into x square by 2, 16.5x minus 6x square. Now we have to find the value of the maximum bending moment. So dmx by dx is equal to 0. So 16.5 minus 12x is equal to 0. From there, x is equal to 16.5 divided by 12. So it comes out to be 1.375 meter. There, let's calculate the moment at x is equal to 1.375. So 16.5x minus 6x square. If you substitute that, you will get that to be 11.344 kilonewton per meter, and that is the maximum bending moment. So M max is equal to 11.344 kilonewton meter. And now we have the second part of the question, that if the diameter is equal to 90 mm, then we need to determine the absolute maximum bending stress in the beam. So absolute maximum, the absolute maximum bending stress is My by I. The maximum bending moment is 11.34 kilonewton meter. So let's convert it in the Newton meter unit. So into 10 to the power 3, what will be the value of Y? Diameter is 90 mm. So this being the neutral axis, the maximum value of Y possible is 45 mm. So 45 by 1000 divided by I, the moment of inertia. The moment of inertia is pi e to the power 4 by 4. So pi d to the power 4 by 4. If you solve this, you will get this to be equal to 158.4 into 10 to the power 6 Newton per meter square. That is 158.4 MPa. So the second part of the question was like, this question is straightforward. How do you locate the point of maximum bending moment? Is you can get an idea from this question. Okay. Now let's move on to the next question. So I'll just pull out the question. You have to determine the dimension A of a beam having a square cross section in terms of the radius. Just hang on for a second. Yeah, I just checked whether this is there in your current assignment. Uh, okay, so you have to determine the dimension A of a beam having a square cross section in terms of radius r of a beam with circular cross section if both beams are subjected to same internal moment, point to be noted, same internal moment which results in the same bending stress. So you have to develop a relationship between, suppose there are two beams, one having a square cross section, one having a circular cross section. Square cross section, the length is the side, the length of the side is A, and for a circular cross section, the radius is R. Both these beams are subjected to same internal moment, which results in same bending stress. You have to find the relationship between A and R so that the bending stress is same. I'll write down the question and then we'll look how do we solve such a question. So this is question number 5. So determine the dimension A of a beam having a square cross section, having a square cross section in terms of the radius r of a beam with a circular cross section if both beams are subjected, if both beams are subjected to the same internal moment, to the same internal moment, which results in the same maximum bending stress. So these are the two cross section. Here the radius is r and the cross section is square with the side length a. You have to develop a relationship between A and R so that it is the bending stress comes out to be equal. So for this, I is equal to pi r to the power 4 by 4 Just hang on for a second. Okay. Okay. This while discussing, I may have uh, I is pi r to the power 4 by 4. And while discussing the previous question, I said pi e to the power 4 by 4. So I correct my mistake. It is pi r to the power 4 by 4. Please correct this. Whatever I've written is fine, but the expression for the moment of inertia. See, while torsion, where you use the polar moment of inertia, that is the moment of inertia about the z-axis. If you like, suppose if this is the slender bar and the z-axis is along this axis, you apply a torsion about this. So I had to be about this axis. So that was polar moment of inertia which you used in torsion. Here you are applying a bending moment. So the moment about, let's say this is the, if this is z, so let's assume this is uh, uh, about this axis. This can be the y-axis. So this is moment of inertia about that y-axis, which is pi for a circular section, pi r to the power 4 by 4. And for a square, it is the moment of inertia is a to the power 4 by 12. Now the maximum bending stress for a square, it is, see, the expression for the bending stress is my by I. The internal bending, same internal moment. So m is the same m. For the square, the value of y is this, which is a by 2, right? A by 2 by I square, which is a to the power 4 by 12. Now sigma max for circle, that is m, y will be equal to r. So r pi r to the power 4 by 4. Now these two maximum bending stresses are equal. So this can be simplified to 6m by a cube. And this is 4m by pi r cube. So in the question, the condition is the maximum stress in a square is equal to the maximum stress in a circle. So 6m by a cube is equal to 4m by pi r cube. So from here, a is equal to 1.677 r. This is the relationship between a and r, so that this condition turns out to be okay. Okay, so let's move on to the next question. Okay, let's move on to the next question. For this beam cross section, I'll just be drawing it. You have to do a number of things. So the cross section looks something like this. Then a shear force V is applied. This length is 125. Okay. This side is a bit shorter. And I'm drawing the cross section and I'll mark the dimensions here, right? So this is 200 mm, this is 30 mm, this is 25 mm, this length is 250 mm, this is 30 mm, this is 125 mm, this point is A and this point is B. So the first thing which you need to do is you have to locate the neutral axis. Locate the neutral axis. Then you have to determine the moment of inertia of the beam cross section about its neutral axis. You have to determine the moment of inertia of the beam cross section about its neutral axis. Then, if the beam cross section is subjected to a shear force of V is equal to 15 kilonewton meter, we have to determine the web's shear stress at A. If the beam cross section is subjected to a shear force of B is equal to 15 kilonewton, you have to determine the web's shear stress at A. Okay, these are the three things which you need to calculate. So first we'll be locating the neutral axis. So the neutral axis will pass through the centroid of the section. So you can locate the centroid of the cross section and the neutral axis will pass through the centroid. So this is the cross section which you have. I'm not redrawing it. So uh, let's assume that we are measuring the neutral axis from the bottom. Okay. So neutral axis we are measuring from the bottom. So y bar is equal to, let's consider the first area, that is, let's calculate in mm. So the area of, I'll just mark with, let's say, blue color, this area. It is 30 into 125, and from the bottom edge, the location of his centroid is 15 mm, so 15 plus, then we have the web. So uh, area is 250 into 25 into its centroid is at a distance of uh, 30 mm because of that flange. So this is 30 plus this much, which is 250 by 2. So 250 by 2 plus 30. Then you have the top flange, which is 200 into 300 into the distance of the centroid, which is this much distance is 15 plus 250 plus 30. So 15 plus 250 plus 30. This entire thing divided by the total area, which is 200 into 30 plus 250 into 25 plus 30 into 125. So if I calculate this, this comes out to be 174.7 mm. So this is the position of the neutral axis from the bottom. Then you have to determine the moment of inertia of the beam cross section about its neutral axis. So, so we can say the neutral axis is passing somewhere. Uh, I'll draw it again here. And this distance is YNA, which is 174.7. So you have to find out the moment of inertia about this neutral axis. So about the centroid of a rectangle, we know that the moment of inertia is bh cubed by 12. And then along with that, I will have to shift the axis from the centroidal axis to the neutral axis. And there I'll use the parallel axis theorem, which is you will have an additional value of a into distance square. So first, let's consider for this flange. So about the centroidal axis of this shaded area, the moment of inertia will be bh cubed by 12. So with this 200, this is 200 and this is 30. So 200 into 30 cube by 12 plus the area, which is 200 into 30 into some distance square. This is the distance between the two axes. So this distance will be, see, first I can calculate this much distance. How much is that much? That distance which I just marked. It will be 250 plus 30 minus 174.7. So 105.3 plus 15. So this is 120.3. So 120.3 square plus you will have for the web. For the web about the CG, it will be the height of the web is 250 mm. So 250 cube into the thickness 25 by 12 plus the area is 250 into 25 into, now the distance of the CG of the web, let's say from the bottom. Here we had calculated that number. It is 125 plus 30, that is 155. So 155 is the distance of the CG of the web minus 174.7. So this will be the distance between the centroidal axis of the web and the neutral axis. So that distance, that is the amount by which you have to shift, plus the lower flange, the dimensions being 125 and the width being 30. So 30 cube by 12. So 125 into 30 into centroidal distance is at a distance of 15 minus 174.7 from the same logic. So if you calculate this, I'll just calculate this. This will be equal to, so it comes out to be, I'll report the answer in meters, 2.1818 into 10 to the power minus 4 meter to the power 4. And here what I was doing, it is in mm. So, okay, this will come out to be 2 1. Okay, so the first part is done. You located the neutral axis. Then the second part is done, that you determine the moment of inertia of the beam cross section about its neutral axis. Then if the beam cross section is subjected to a shear force of V is equal to 15 kilonewton, you have to determine the web's shear stress at A. So for that, you will be using shear stress is equal to VQ by I into T. Shear force is given to be 15 kilonewton. So 15 into 10 to the power 3. Now what is this value of Q? The value of Q will be, this is the cross section. This is point A. So point A. So this is the cross section. So this is the shaded area, and suppose this is the neutral axis. So we have to take moment of area of the shaded portion about the neutral axis. So let me calculate Q here. Q will be the y bar distance into A. What will be the distance y bar? It will be this. It will be, see, from the bottom, the neutral axis is at a distance of 174.7. So from the top, I had in the previous part, I had calculated that this y bar will be 105.3 plus 15. 105.3 plus 15. So it is 120.3. So 120.3 into this area, which is 200 into 30, which comes out to be 721800 mm cube. So just substitute here. 721,800 mm cube. This is in Newton. I is this number, which is just substituted to 18181,773.3 mm to the power 4, and T, the thickness of basically the width of that section. Here, the width of that section, we know that this width is 25 mm. See, 25 mm. So use that. So 25. So whatever you will get from the units, you can see it will be in Newton per mm square. So just calculate it. So this is equal to 1.98 Newton per mm square, or 1.98 MPa. Okay. I hope this question is also clear. So these were mainly the questions which I had today. We still have some time. I'll try to uh, find a small question which we can win this time. So a quick question, a small question. So this will be question number 7. So I have a steel beam which is 25 mm wide and 75 mm deep. It is pinned to supports at points A and B like this. So I have a beam like this, which is been supported at this point, and there is a roller at this point. This is X. This is point A and B. Here and here I have 5 kilonewton load acting. This length is zero point 0.3 meter. This length is zero point 0.3 meter, and this is 1.5 meter. So we know that the system is symmetrical, and just by looking I can tell the reactions are 5 kilonewton and 5 kilonewton. And here the cross section of the beam is given. I'm drawing an exaggerated view. This is the y axis. This is the z axis. This is the height h and the width b. Width b is 25 mm. Height h is 75 mm. Under this loading, we have to find out the maximum bending stress at the midspan of the beam. Find the maximum bending stress at the mid span of the beam. So first, let's draw the bending moment. This is point A, this is point B. You have a 5 kilonewton load. So in the overhang, the bending moments will be, the value will be 5 into zero point 0.3, that is 1.5 kilonewton meter. Same on this side, 1.5 kilonewton meter. And you have a constant bending moment inside. So this is the bending moment diagram. So the maximum bending moment is 1.5 kilonewton meter. Now maximum bending stress is M into Y by I. So maximum bending moment is 1.6 into 10 to the power 6 Newton mm. This is how I'm substituting. Okay. Y will be, if this is the neutral axis, this is Y is equal to h by 2, which is 75 by 2, and moment of inertia will be bh cubed by 12. B is 25. It is bh cubed by 12 because you are taking Iz, or the moment is being applied about the z axis. Then the formula, uh, like bh cubed by 12, like basically you cube the value, and like here there is a cube on the number 75, and 75 is the height of the section because the moment is about the axis z, and the axis z is cutting that uh, uh, side. You can remember it like this: 75 cube by 12. This is in mm, this is in mm. So your answer will be Newton per mm square. Just plug in the numbers and calculate it. So 1.5 into 10 to the power 6 into 75 divided by 2 into 12 divided by 25 divided by 75 to the power 3. So this comes out to be, this comes out to be 64 Newton per mm square, or 65 MPa. Okay, this is the bag of questions I had today. If you have any doubts, you can ask. If you have any doubts in the assignments which have been given earlier, or you find any, if you have any confusion in the solutions which I have provided, all these notes are uploaded, which I do in the tutorial. If you find something which you can which you can't understand, if, or if you find something is not correct, please do drop an email. My email ID is Sukanya, SUKANYAK21 at the rate iitk.ac.in. So I'll be happy to help you. If you have any doubts, you can ask. Um, Thank you for attending the session. I'll close the session.